you can't look at this, not understand that this is the worst clinical trial data ever presented, then I don't know what lesson in statistics or medicine you need. But let me help understand. The only thing you really need to look at is up to here. The rest don't matter. In medicine, this is the only thing we look at. This is like, Harv's a poker player. So am I. This is like playing what they call after poker. This is what we called it in prison. But I've heard different terms for it. Let's say you got, okay, here are your 2 cards, my 2 cards, and you say, all right, I don't know, I have ace of clubs, king of diamonds, and you got 2 sevens. Not a bad hand. What is this, about a 50-50? I think it's 60-40 I'm going to win. So I don't know, you bet. I put 40 in the pot. You put 40 in the pot. You call my bet. Great. This is a special kind of poker. We don't have to worry about the rules too much. All right, first card comes out. It's an ace. Next card comes out, and the next card comes out. This is sometimes called a flop. And this is a 2, and this is a 4. I can't see your cards, right? Because we're playing poker. But I see my ace, and I say, you know what? I'm probably winning here. I'm gonna bet $500. And you say, nah, I'm out, I fold. He's probably got the ace. I don't have the sevens. I only have sevens. I'm beaten on this ace. There's no chance these next 2 cards come down. So we start to clean up the cards. The dealer starts to clean up the cards. I start to get my chips. And you say, no, wait. I want to see what cards they would have been. And of course, the cards they would have been were a 6 and a 7. And you said, oh, man, I would have gotten trips. I shouldn't have done that. And I'm sitting here looking at my $40 that I took from you. I'm like, okay. So this is irrelevant because of the numerical difference. So 𝐴'S_COG, yeah, let me explain the numbers. The 𝐴'S_COG score, this is not shown here for a reason. It goes from 0 to 70. Okay? So after 6 months, with this drug, you gained 0.6, 0.6 versus the placebo. So you did better on drug than placebo by 0.6 points. But you started with something like 20-something points. And this is not a material amount. How do we know it's not a material amount? Well, the standard deviation is also not shown. There's a very simple calculation for this, actually. Multiply the standard error, 0.786, multiplied by the square root of the full analysis set. Square root of the full analysis set is square root of 155 is 12.5, and we multiply that by 0.786, and you have a standard deviation of 10. Okay? So in our little clinical trial here, your baseline is, say, 20, and the standard deviation is 10. So it's important to get the perspective, because you might say, well, Martin, I'd much rather have 0.6 than 0. And that's right. If I had Alzheimer's, if I could get a reliable 0.6, I would take it. But is that a reliable 0.6? Well, it depends.
Autofilled.
Sometimes it is, and sometimes it isn't. We use something called statistics to figure that out. And I've done this a million times, so I have a little experience here. But in statistics, we can use standard deviations, standard errors, and p-values to figure this out. Okay, so if I threw 10 coins, and I got 6 heads, 4 tails, I have a mean of 0.6, and a pretty high standard deviation. So another way to do it would be if I threw ten dice and I summed the dice, and we had a game as to whether or not, I don't know, the sum of the dice would exceed, say, 30. And I threw 10 dice, and the average dice throw was a 4.1. So over 10 dice throws, they added up to 41. And you might say, well, that's pretty good. Threw 100 dice, and the average was 3.65. They added up to 365. There's a 1, 2, 3, 4, 5, 6 on the die. You throw out the last two, the first two, and you get 3.5 would be the average. So over time, this should approach 3.5. That should be the average. But you might say this was a good dice. This is a lucky dice. But you would be wrong. How many dice throws would it take before you would convinced that you'd had a lucky dice or a bent die or a fixed die, a weighted die? Well, if you did 1,000 and it was 3.8, it was 3812, let's say, you might start to ask yourself, is this a fixed die? And again, there's a way to do that. It's called rejecting the null hypothesis. And the p-value has to be less than 0.05. There's a number of ways to calculate this. Popular one is called the t-test. When you can calculate to 0.05, you can say, I can reject the null hypothesis that the die is not weighted. I can reject that null hypothesis with a certainty that my probability that this result was by chance was less than 0.05. If the p-value is 0.01, there's a 1% chance that this result was due to chance. That this result, not another result, not the main result, but this result rejects the p-value, rejects the null hypothesis with this amount of certainty. Now, this is not always easy to understand. So when you see this and you say, wow, 0.06 is better than nothing, there's a problem here, because the patients come in with, say, 20, 25, 15. There's a huge standard deviation. They're points. I'll just draw the points to show you the standard deviation. Something like this. Okay, and they don't, here's some arrows. Some of them move up. Some of them move up a lot. Some of them move up a little. Some of them move up a lot. Some of them are sort of flat. And some of them move down. Okay, so we have the new points here. And we add them up. And we say, well, the average of these guys was 24. And after 6 months of treatment, they were 24.3. And you do the same with placebo. And you saw that they were 24. Again, this is the drug, 24.3. And on placebo is 24 to 23.7. And the odds that this was because the drug was effective is 48%. In medicine, we need a close to 100%. The odds that we can reject the null hypothesis are very low. We need more certainty. You can say that this was likely to be due to chance. 48% of the time, this is what would happen if you just did an experiment randomly. That doesn't mean, by the way, that there's a 48% chance the drug works. That's the wrong interpretation. All this means is there's a 48% chance that the null hypothesis, which is the drug does nothing, can be rejected. Or the drug does something. it does not mean that there's a 52% chance that the drug does something. We have to be able to reject the null hypothesis with strong percentage, that there's a 1% chance the drug does nothing, or less. In a lot of drugs, it's 0.0001. So the reason the percent of slowing thing doesn't make any sense is you're saying slowing decline was 38%. Well, if I said I had 24 and I went to a decline of 23.995, and then with the placebo, it was 24 to 23.990. This is a 50% slowing of decline. This is even better, technically. But you would agree with me that that number doesn't make any sense to look at. It just sounds good, right? That doesn't make any sense, because you're not slowing the decline if there is no decline. So it really doesn't stand to reason there. So the only thing we really have to look at is, did the drug make you better? And again, this is better understood in the standard deviation, which is roughly 10. So you get half a point on a, normally you're swinging around 10 points. And 10 points is not exactly, it's not much, it's a lot relative to getting half a point. Because if you're getting half a point on 10 points, well, I mean, are you really doing much to my disease if I'm going to be swinging 10 points? It's a 70-point scale, okay? And I'm going from 20, inevitably I'm going to go to 70 someday. So getting me half a point isn't doing much, and the certainty that that half a point is actually coming is basically very uncertain. A couple more patients and it would have changed. And remember, this is a company that's known to mess around a little bit with data. They've done that before. So the chances, in my experience, when you see something like this and you look for, oh, well, maybe we'll get half a point again. Well, let me show you actually what happens typically. You're gonna like this. Put down a bunch of times this has happened. And you can see each time in phase 2, Dimebond had 4 points. Well, in phase 3, they had 0.1 points. All right, well, what about Vivek's drug? That looked okay. It had 1.3 points, more than Cassava's. What happened in reality? Oh, just 0.4 points. It didn't work. Drug dead. How about bapineuzumab? That was a 30 billion market cap at one point. 2.3 in phase 2 became only 0.3 in phase 3, and that drug died too. Donanemab shrunk even, but donanemab had so many patients and a good variability in standard error that they kept it going at 1.3. And lecanemab met at 1.5. But here, you are literally working with 0.56. You cannot go lower. I mean, think about how low that is. Why would you even try? I almost bought this drug that Vivek bought. A lot of people said, why try? What's the point of getting 1.3 𝐴𝑑ES-COG? That's not good. Patients may not even take it 1 point. So what? I need 10 points. I need to slow 5 points, something like that. So cemipalam is going to go from 0.6 to what? 0.3, 0.2, 0.1, negative? Well, with placebo, we know placebo gets you 0, right? Because that's the worst it could be. So it's got to be something between 0.6 and 0.0. Well, we know that lecanemab and donanemab have had trouble selling because people say a point isn't worth it. So 0.3 is even less than these guys, 0.2. And you don't have the statistical power to see that. To see that small of a difference is very, very hard. For example, in our dice thing, I can say very quickly that a dice is fair if you grant me that I'm saying that this dice is fair within 40 to 60%, or this coin, I should say. Let's do a coin. This coin is always going to be within 40 to 60%. And again, I can never say something with certainty. It's always within error bound. I could say with 1% certainty of the null hypothesis, so 99% certainty, I can say that this dice will go from between heads and tails between 40 and 60% of the time with, say, 500 samples if the result, the mean, mu, is between 0.45 and 0.55. Now, I don't know the actual statistics, but I could calculate it easily. But if the mean came up as 0.7, I would have a harder time saying this is a fair dice because it's outside of a confidence interval that I'm comfortable with. And here's the confidence interval that Cassava says this drug is between 95% chance it's between 2 points and 1 point. So 2 points, this is a probability distribution, right? Somebody was talking about distributions earlier. They are saying within 95% that this drug is within -2, which is 2 points better than placebo, but also could be as bad as worse than placebo by 1 point. And that's why our average that we did see was 0.56. But they understand that because of the small sample size and the high variability, that it actually could be anywhere in between. 0.65, I think it was, or 5.6. It could be anywhere between 0.56 all the way up to -2, which would be better, all the way up to +1, which would be worse. You could not, after here, right, anything in this area would be FDA rejection, right? Because you can't have a drug worse. Nobody would use a drug that's worse than placebo. So if it's anywhere in this part of the distribution, it's over. And again, I would contend that even at 0.5, you have a trouble here. It has to, by luck, sort of end up in here next time they do a trial. But you lose luck as the sample size goes up. This is going to go from 150 patients to 900 patients. So the chance they replicate this is unlikely. If you ask me, what I think happens is a drug that doesn't work will be 0. And this should make a lot of sense to you guys. A drug that doesn't work at all. I'll give you a sugar pill, right? This is 0. This is versus patients, right? So above here is good, down here is bad. Well, you give one patient the drug, he might have done okay. And you give 2 people the drug, they might have done bad. And you have 3, and what ends up happening? There's a central tendency. It approaches 0. And these little blips, these tiny blips, as you zoom in, the blips get smaller. And as you zoom in, the blips become pixel-sized. These blips are like the 0.65 they saw. Take out 1 or 2 patients, they would have been negative. So they're taking this blip and saying, wow, this is a good blip, isn't it? Well, no, if it was up here somewhere, that'd be good. Or if the data looked like this, little blip in the beginning, and then a little blip in the beginning, and then it sort of was like something like that, and a bunch of little mini blips in between. Well, then you could say, okay, clearly it's approaching this maybe asymptote, maybe blips like this, whatever it is. You can see the blips and say, okay, the statistics are showing it's approaching this +2, but that's not what's happening here. If you look at the individual data, and this is just for mild, you can see that the data is sort of all over the place. So getting a half a point is really not too useful. So anyway, there's some thoughts on Cassava. I'm still writing this thing up, so bear with me. I'll have the full book out soon.
Both studies have the same efficacy.
This woman has a PhD in bench neuroscience, but she does medicinal chemistry with no crystallography, and she's doing clinical work, designing clinical trials.
Refocus includes sub-studies for...
Now me, I've done all that. And then some. I started my own biotech, took it public at 28. Hit $1 billion. Yeah. Then I started another one. I was on my way to $1 billion until some haters showed up. Now I got a new company and I'm on my way to $1 billion again. Again. And oh, how many times have I predicted biotech's going zero? All the time. That's what I do. All the time. A lot of you forget. But some of you are old enough to remember Axovant. Some of you are even older to remember Vital. Or some of you worked with me and you were there when we did Celadon. Or maybe you're even older than that and you remember when I torched Mankind. Rest in peace, Mankind, man. I had to do it to him. But don't take it from me. Cassava will tell you how their drug did in a few weeks. Don't take it from me. You'll see. You guys coming brand new to biotech. Oh, this stock looks good. Let me see how this goes. Boop! I don't want to do biotech anymore. But it's good in mild subgroup with patients who have aphasia. So let's do another trial in aphasia. Why is the stock down 83%? Bag holders, bagatocin. You have a heavy dose of bagatocin
autofill
and bagatonin. Bagatocin is a peptide similar to oxytocin, but you get it when you're a mega bag holder. It's released in your brain. Bagatonin is the baggy derivative of serotonin, which is released when you lose all your money to me.